Hello and welcome to our Converting Indirect Control Flow to Direct Control Flow in C Programs research project presentation for systems and software security. Introduction. Let's set the stage with a fundamental concept, the execution of a program. At its core, a program, whether it's a simple utility or a complex application, is a series of instructions that the computer follows in a specific order. Think of it like a meticulously crafted recipe. Each step must be performed in the correct sequence in order to achieve the culinary outcome. Similarly, in a program, the execution which instructions are executed are what we call the control flow, and it is paramount to correct operation that the control flow follow the expected outcome. Our project is motivated by a critical security challenge that plagues software systems, vulnerabilities arising from indirect control flow. Specifically, we are concerned with the ways in which attackers exploit these indirect control flow mechanisms to compromise the integrity and security of a program. A key area of focus is the exploitation of function pointers. To understand this, let's define what these are. Function pointers are essentially variables that, instead of holding data values like integers or characters, hold memory addresses of functions. This capability to store and manipulate function addresses provides a powerful mechanism for dynamic function calls, allowing a program to determine which function to execute at runtime. Does come with a caveat. It introduces vulnerability. If an attacker can successfully overwrite the value of the function pointer, they can change the memory address to then redirect to some other location that they get to define, potentially a malicious function. This is a severe security risk, as it allows the attacker to hijack the program's control flow and gain unauthorized control over its behavior. And our project's core objective is to provide a solution to that problem. We designed a Python program to automatically analyze C code and identify common indirect control flow constructs, and then convert them to direct control flow. Before we begin, let's talk about our agenda. First, we'll be discussing what is control flow and its importance in relation to security. Then we will be discussing our Python code, giving a live demonstration, and then finally talking about the limitations and potential future path of our work going forward. Control flow and security. To fully appreciate the security implications of our project, we must first establish a clear understanding of what control flow signifies in computer programming. At its most basic, it is the defined order in which a computer executes the individual instructions that constitute a program. Imagine a complex machine with numerous levers and gears. Control flow dictates precisely which lever is pulled and in what sequence to achieve the desired outcome. In the realm of programming, this sequence is not arbitrary. It's meticulously determined by special statements within the code itself, called control statements. These statements act as the traffic signals of a program, guiding the flow and execution and dictating which path the computer takes through that code. As you observe in this diagram on the screen, there are broadly three types. The first are conditional statements such as if and else, and switches. The second consists of iteration statements such as for and while loops, and the third is jump statements such as break and continue. Now that we have established a foundational understanding of control flow in general, let's turn our attention to a specific category. Direct control flow is characterized by a crucial feature. The target of any jump or function call is definitively known at compile time, refers to the stage when the source code of a program is translated into machine-readable instructions by a compiler. This known target characteristic of direct control flow contributes significantly to its inherent safety. Because the compiler possesses complete knowledge of where the program will jump or which function it will call, it can perform various safety checks. These compile time checks help to prevent a wide range of errors and vulnerabilities that could arise from unexpected or invalid control flow transfers. Let's illustrate the direct control flow with some common and familiar examples from C programming. Consider the if statement. This fundamental conditional statement allows the program to choose between two distinct blocks of code based on the evaluation of a specific condition. The compiler can analyze the code and determine precisely which of the two blocks will be executed depending on the truth or falsehood of the condition. Another example is the for loop. This loop provides a mechanism for repetitive execution of a block of code for a predetermined number of iterations. The compiler can analyze the loop's parameters and determine the exact sequence of execution, including the number of times the loop will iterate. Finally, let's look at the while loop. Similar to the for loop, the while loop allows for repetitive execution, but the repetition continues as long as a specified condition remains true, although the exact number of repetitions might not be known at compile time. In summary, direct control flow offers a high degree of predictability and safety due to the compile time determination of execution targets. Moving on from the relatively safe realm of direct control flow, we move to the more potentially problematic realm of indirect control flow, where the defining characteristic is that function calls and jumps and that like are not necessarily determined until runtime. In contrast to compile time, where decisions are made before the program executes, runtime decisions are made as the program is running. Prime example being the use of function pointers. But what is a function pointer? Essentially, they are variables, but instead of holding a simple data value, such as an integer or character, a function pointer holds the memory address to a function. The capability to store these memory addresses allows for dynamic function calls, which allow a program to decide at runtime which specific functions to execute. This is in contrast to direct function calls, where function to be called is in a fixed location, which is known at compile time. To illustrate this with an example from C code snippet on the slide, void func pointer declares a variable named func pointer with the pointer syntax, indicating that func pointer is a pointer to a function that takes no arguments and returns void, as in no values returned. Func pointer equals some function assigns the memory address of that function named some function to func pointer. And then when func pointer is called as a function on that last line, it is instead indirectly calling some function which executes the code within some function while having it accessed as func pointer. The power and flexibility of function pointers are undeniable. They enable advanced programming techniques such as callback and dynamic dispatch. However, because function pointers hold memory addresses, they become potential targets for attackers seeking to manipulate program behavior. Now we arrive at the core security concern that motivates our project: the vulnerabilities associated with indirect control flow, specifically the threat of control flow hijacking. Represents a class of security attacks that exploit weaknesses in program design or implementation to deviate the program's execution from its intended path. Attackers aim to seize control of the program's execution flow, forcing it to execute code of their choosing. This malicious redirection of execution can have severe consequences, potentially allowing attackers to execute arbitrary commands on the system. The vulnerability of indirect control flow to hijacking systems stems from its very nature. The target of execution is determined at runtime. To illustrate this, let's consider the specific case of function pointers as shown on the slide. If a program uses function pointers and an attacker can find a way to overwrite the memory where a function pointer is stored, they can change the function that will be called. Instead of calling a legitimate function, the program will jump to an address specified by the attacker, which could point to malicious code. On the slide, you can see two common attack vectors used in these control flow attack hijacking: buffer overflows and other memory corruption bugs. In summary, control flow hijacking poses a significant threat, and indirect control flow constructs like function pointers are a prime target for attackers. To truly understand the significance of our project, it's crucial to focus on the primary example of indirect control flow, function pointers. As we've discussed, they are variables that store the memory address of a function, enabling dynamic function calls. Let's emphasize both the power and potential danger associated with function pointers. They provide great flexibility, allowing implementation of advanced programming techniques that would be difficult or impossible to achieve with only direct function calls. Callbacks are one such powerful application. They involve passing a function as an argument to another function. This allows a function to call back to code provided by the user or another part of the program at a specific point in its execution. Incredibly useful for event-driven programming. Another key application is dynamic dispatch, which is a mechanism used in object-oriented programming to determine which specific implementation of a method to call at runtime based on the actual type of the object. Very useful and enables polymorphism and other object-oriented features. In general, function pointers allow for highly customizable and extensible code. There is risk, however. The flexibility comes at a cost, as they are prime targets for attackers. The very features that make function pointers so powerful is also what makes them a significant security risk. Because they hold memory addresses, function pointers become attractive targets for malicious actors seeking to manipulate program behavior. If an attacker can find a way to overwrite memory where a function pointer is stored, they can effectively redirect a program's execution flow And instead of the program calling what the programmer intended, it can be tricked into calling what the attacker intends. If a function pointer is corrupted, the program can jump to any memory location. This arbitrary jump can have devastating consequences. In summary, while function pointers are a valuable tool for programmers, their inherent flexibility introduces a significant security vulnerability that must be addressed. Program explanation. To provide a high level of understanding of how our Python program operates, we can break down its core logic into 4 direct and sequential stages. The first is the parse of the C code. This initial stage involves taking the raw text of the C program that we wish to analyze and transforming it into a computer-readable representation known as an abstract syntax tree, or AST. Think of it as a hierarchical diagram that meticulously captures the grammatical structure of the C code, but arranged in a tree format easily read by a computer. The second stage is analyze AST. This is examining the tree-like representation to extract relevant information. This involves traversing the AST, examining each node to determine whether it represents a function pointer declaration, a function call, or any number of other events that we're also searching for. The third most critical stage is transform AST. We now modify the AST to replace these constructs with their direct control flow equivalents. And the final stage is to generate the modified C code. After the AST has been transformed to remove indirect control flow, we now need to convert it back into compilable C code. By following these 4 distinct stages, our Python program automates the process of converting C code to mitigate the risks associated with indirect control flow. The core functionality of our Python program is encapsulated within the C converter class. This class serves as the central orchestrator for the conversion process, managing the various stages involved in analyzing and transforming our C code. Let's begin by examining the constructor method init. Its primary purpose is to initialize the object's internal state, setting up the necessary data structures. The first of these is self.functionPointersVar. Function pointer var is a set. In this context, function pointer vars will be used to store the names of all the function pointer variables that our program identifies within the C code being analyzed. Next, the constructor creates a C generator object. The C generator object is not part of our own code, but is a utility provided by PyCparser library, a powerful Python library that we leverage to parse C code and generate ASTs. The C generator's role is opposite of parsing. It takes the AST as input and generates C code from it after our modifications have taken place. Finally, the init method initializes self.ast cache. This is another attribute of the C converter class, this time a dictionary. It will be used to store previously parsed AST. The keys of the dictionary will be hashes of the C code, and the values will be the corresponding ASTs. This allows for if we encounter the same C code again, we can retrieve its AST from the cache instead of reparsing it. Now that we've covered the initialization phase, let's delve into the crucial step of analyzing the abstract syntax tree. The analyze AST function is responsible for initializing this analysis. This function takes the AST as input, and the objective is to systematically examine the AST and identify occurrences of function pointers within the code. The AST nodes represent different elements of the C code, such as function definition, a variable declaration, or an expression. Analyze AST begins by iterating through the top level nodes of the AST, which typically correspond to function definitions. For instance, in the simplified AST snippet showed on the slide, you can observe funcdef nodes representing the functions foo and var. For each function definition encountered during this iteration, analyze AST calls another function, collect function pointer info. The purpose of this method is to recursively explore the function's body to locate any function pointer declarations. The function body is typically represented by a compound known in the AST, which contains a sequence of statements. The ability to accurately identify function pointers within the C code is fundamental to our program's operation. This task is accomplished by the helper function isFunctionPointer, the primary responsibility of which is to examine a given node within AST and determine whether that node represents a function pointer type. To achieve this, it performs a series of checks on the structure of the AST node. First, it checks if the node is an instance of pointer declaration. Since the function pointers are by definition pointers to functions, this criterion must be met. Second is function pointer proceeds to check the type of the pointer. Specifically, it verifies if the pointer's type is an instance of funcdecl, or function declaration. This check ensures that we are dealing with a pointer to a function as opposed to a pointer to some other data type. IsFunctionPointer returns true only if both of these conditions are satisfied. Let's illustrate this with an example C code snippet provided on the slide. Looking at the second line in the example, there is a declaration of a function pointer named fp. Void indicates that the function pointer has no return value. The asterisk fp signifies that fp is a pointer, and the two parentheses at the end with nothing in them indicates that the pointer points to a function that takes no arguments. When our program processes this declaration, the function will correctly identify fp as a function pointer because it matches both the pointer declaration and function declaration patterns in the AST. In essence, isFunctionPointer acts as a precise filter, enabling our program to accurately pinpoint function pointers. The collectFunctionPointerInfo function plays a crucial role in our program's analysis of C code. It systematically locates and records function pointer declarations within the AST. It recursively traverses compound nodes within the AST. In the AST structure, compound nodes represent blocks of code. These blocks can appear in various contexts within C programs, such as within function definitions and loop bodies. By recursively traversing these compound nodes, collectFunctionPointerInfo ensures that it examines all the code within a function. These compound nodes allow it to specifically search for declared nodes in the AST represent variable declarations. Since function pointers are declared as variables, these declared nodes are locations where we expect to find them. For each declared node that it encounters, collectFunctionPointerInfo utilizes the isFunctionPointer helper we just discussed to determine whether the declared variable is indeed a function pointer. If isFunctionPointer confirms that a declared node represents a function pointer, we take the variable's name and add it to function pointer vars, the structure for storing function pointers, which allow us to maintain a record for all the function pointers found within the code, which will be essential for the subsequent transformation stage. A key aspect of the function's functionality is its recursive nature. It doesn't just examine the immediate statement within a compound node, it also calls itself recursively for any nested code blocks crucial for handling function pointer declarations that occur within nested scopes, such as inside if statements or loops. In summary, collectFunctionPointerInfo is a function that systematically explores the AST representation of C code to identify and record all function pointer declarations, ensuring that even those within nested code structures are properly detected. Now we arrive at a pivotal stage in our program's execution, the transformation of the AST. Transform AST is the function that is the core component responsible for this transformation. Its primary objective is to modify the AST by replacing these indirect calls, which can be manipulated by attackers, with safer direct function calls. The function operates by iterating through the function definitions within the AST. For each funcdef node encountered, it transform AST invokes another crucial function, track assignments in block. The track assignments in block function plays a vital role in analyzing how function pointers are used within the code of a particular function. It tracks assignments to function pointers, determining which function is currently assigned to each pointer at different points in the code. It also examines function calls that are made through function pointers. By carefully tracking these assignments and calls, track assignments in block enables transform AST to make informed decisions about replacing indirect calls with direct ones. If track assignments in block can definitively determine the target of an indirect function call, then transform AST performs. The replacement involves modifying the AST to replace the indirect function call with a direct one to the known target function. In essence, the transform AST ensures that function pointer calls are resolved to direct function calls whenever it is possible to do so, enhancing the security of the code by reducing its reliance on vulnerable indirect control flow mechanisms. The track assignments in block function plays a critical role in accurately tracking how function pointers are assigned values and how they are used in function calls within a given code block. The function takes two key arguments, compound node, which is an AST node for a code block within the C program, and assignment state, which is a dictionary that serves as a dynamic record keeper, tracking which specific function is currently assigned to each function pointer at any given time. The track assignments in block function operates by iterating through each statement within the compound node. During this iteration, it performs the following key actions. Tracking assignments. If the function encounters an assignment statement where a value is being assigned to a function pointer, it updates the assignment state dictionary. This ensures that the function keeps a real-time record of what each function pointer is pointing to. Transforming function calls. If the function encounters a function call that is being made through a function pointer, it consults the assignment state dictionary. If the assignment state dictionary contains an entry indicating that the function pointer variable currently points to a specific function, the track assignments in block function replaces the indirect function call with a direct function call to that specific function. Finally, handling nested blocks. To handle nested blocks, track assignments in block uses recursion, When it encounters a nested code block, it calls itself recursively to analyze that nested block. Crucially, when making this recursive call, it passes a copy of the assignment state dictionary. This ensures that changes made to the function pointer assignments within the nested block do not incorrectly affect the analysis of the outer block. We also have a system for removing returns from functions, as these are also indirect. We achieve this by identifying the return statement. Once that is done, we convert the function from its original data type to a void and prepend a pointer variable to the list of parameters, ensuring that the variable name is unique. We then take the value that would have been returned and assign it to the variable. Then at every function call, the variable that would have been the assignment from the function will be passed as a memory reference instead. Our program incorporates essential steps for code preprocessing and generation to ensure smooth, effective conversion process. The preprocess C code function plays a role in preparing the input C code for parsing. However, it's important to note that this function performs only minimal preprocessing. Its primary focus is on cleaning up the code by addressing formatting inconsistencies, such as removing extraneous white spaces. Cleanup helps to ensure that the code adheres to consistent format, which can simplify the subsequent parsing stages. By ensuring the code is well formatted, it helps improve the robustness of our program. The convert function serves as the central orchestrator, bringing together all the different components of the program to perform the complete conversion. This function represents the main entry point for external code uses to initiate the conversion process. It takes the raw C code and initiates the following sequence of operations: calling all the necessary functions for parsing, then calling all the necessary functions for analysis, then transformation, and finally code generation. In addition to these core operations, the convert function also incorporates robust error handling using a try except block to prevent the code from crashing. In summary, the code preprocessing and generation stages implemented by preprocessing C code and convert functions are crucial for preparing the C code for analysis and for producing the final transformed C code in a robust and reliable manner. Our program incorporates mechanisms for both error handling and optimization, which are crucial for its robustness and efficiency. In error handling, the convert function includes a try and except block. If an exception is caught in the try, the except block is executed, allowing the program to handle the error gracefully instead of crashing abruptly. In our program, if any error occurs during the parsing, the analysis, the transformation, the except block will catch the corresponding exception. The program then returns an ideally informative error message to the user. In optimization, to enhance the performance of our program, it employs a caching mechanism. The AST cache, which is a dictionary initialized in the init method, is used to store previously parsed ASTs. The keys for the dictionary are MD5 hashes of input C code. The values stored in the dictionary are the corresponding ASTs that were generated from the C code. When the convert function is called within a given C code input, it first calculates the MD5 hash of that code, then checking if this hash already exists. If the hash is found in the cache, it means that the program has previously parsed this exact same C code. In this case, the program can simply retrieve the pre-existing AST from the AST cache instead of reparsing the code from scratch. Parsing can be computationally expensive operation, so retrieving the AST from cache significantly speeds up the conversion process. In summary, the error handling and optimization techniques implemented in our program contribute to its robustness, user-friendliness, and performance. Now, we will move on to a demonstration of our code.
Okay, so I am going to do our demonstration. So I have all of our code and benchmarks loaded up into a Google Colab document, separated into different sections just for ease. So this is our code here. We have one big class called C converter, and inside of that class we have many different functions, but the first part includes a library called PyCParser, which parses the C code into its AST, and then we have a function that analyzes the AST and analyzes all of the individual functions that are broken down in the AST. Then we have additional functions to transform that AST and then to rewrite the code using only direct control flow instead of indirect control flow. So our code supports both reading in C code files and also putting in the C code directly. So for this first example, I have this file here of C code, which is just a very basic program. It has two functions called foo and bar, and function foo just prints foo, and function bar simply prints bar. However, I use function pointers to actually call those functions inside of the main function rather than just calling the functions directly. So this code takes in an input, and if that integer that is being inputted is 0, it runs foo, or else it runs bar. So this is the initial C code here. And then if you look at the transformed C code after running our program, you can see that the function has been called directly inside of the main functions rather than using these function pointers. So fp equals foo was just changed to a direct call to foo inside of the first if block, and fp equals bar was just changed directly to bar inside of the else block. Now for our second code, that was also a first iteration of the code. That was our first big iteration of the code. So it still has a return statement at the end. Our second example that I have to show you now it's the same code, but it adds some processing to convert return statements into a pointer variable, which then gets added as a parameter into the main function, since returns are considered to be in direct control flow. So that is this added function here at the end. And the code is also inputted into the program directly instead of as a file in this example. So here I actually have two examples. One is C code 2. This is the same code as what I just showed being passed in as a file. But then I have C code, which is actually a do while loop, and it also has for loops as well. So this will work for nested for while loops and also just for and while loops by themselves. So you can see for the C code 2, which is the same as we had before, the only difference is now that it does not have a return statement. Instead, it has a star out is equal to the output, and that is added as a parameter to the main function to get around the issue with the return statements. And then for the C code, which is a do while and for loop. So you can see we have a nested while loop inside of a for loop, and then we have a do loop as well inside of the for. And you can see that for the output after running our program, the functions hello and nested are printed directly. Those are also just functions that just print. Function hello prints hello, and function nested just prints nested. So they're also just very basic print functions, because what the functions do has nothing to do with the objective of this program. But you can see the function pointer calls are removed and the functions are simply called directly while maintaining the integrity of the program. Anyway, this demonstration was simply supposed to show that this approach of converting indirect to direct control flow using an automated program to edit the code rather than doing this at compile time is a viable approach, and definitely more research should be done into this field. Thank you very much.
It is important to recognize limitation of our current program. Even though it makes strong progress in mitigating indirect control flow vulnerabilities, first, the program mainly targets function pointers, which are a major source of such vulnerabilities. However, it doesn't handle other forms of jump tables used in some switch statements. Second, it lacks full semantic analysis. It relies on syntactic patterns in the AST, which works for many cases but can be bypassed by confused code. Semantic analysis understands the actual behavior of the code, which is needed for more robust detection. It assumes the code is relatively simple. It struggles with complex C codes, which can break its parsing and analysis. Fourth, it doesn't cover all function pointers assignment cases. It works well with a function but may fail when pointers are passed or returned across functions. In summary, while the tool is valuable, knowing its limitation helps ensure proper use and informs future improvements. For future work and improvement, to continue improving our program, we have identified several areas of future work. First, we plan to expand support to other indirect control flows mechanisms like jump tables, which is commonly used for switch statements, beyond just function pointers. This will broaden the program's applicability across more C code patterns. Second, we want to add more robust semantic analysis. Right now, we rely mostly on syntactics, but adding a data flow and control flow analysis will help us better understand complex code and resist complexion. Third, we aim to improve error handling and reporting. More detailed message will help users identify and resolve issues more effectively. Fourth, we will develop a comprehensive test to ensure correctness and reliability across a wide range of C constructs. including edge cases. Lastly, we plan to handle function pointers passed as arguments or returned from function, which will allow us to better support a real-world C code. This enhancement will make our program more powerful and reliable for securing C code against indirect control flow vulnerabilities. So to recap, we built a Python tool that transforms C code by converting indirect control flow using function pointers into direct calls. This is the core of our project and what makes it valuable. This reduces a serious security risk. Direct calls are harder to hijack, so this helps protect C programs from control flow attacks. Yes, there are limitations, but this is a strong first step. Our tool isn't perfect, but it sets the stage for future improvement and deeper protection. In conclusion, our project offers a practical way to make C code safer and opens the door for more advanced research in securing low-level systems. Thank you.